Hi everyone. So in this video, we're going to be continuing to learn about transformations of sine and cosine. Specifically, we're going to be focusing on horizontal transformations. So horizontal stretches and compressions, as well as horizontal shifts, and then kind of seeing how all the different transformations fit together. So overall, I think the examples in this video are going to be a little bit trickier, but I have a lot of examples put together to give us a good amount of practice with this. So last time at the beginning of the video, I showed you this table that I typically give students in my pre-calculus 1 classes that kind of summarizes all the different types of transformations. And one of the ways that you can kind of separate or categorize transformations is by whether they're vertical or horizontal. And so a vertical transformation is a transformation that changes the outputs, the y coordinates of a graph. Whereas a horizontal transformation is a transformation that changes the inputs, the x values, or in this case, the t values of your function. And so the way that you can determine whether your transformation is going to be vertical or horizontal is basically, are you making a change to the function as a whole, or are you making a change to your input variable? And so if you're making a change to your input variable, that's going to be a horizontal change, a horizontal transformation. And so by adding or subtracting, by negating, by multiplying your input variable, that's going to give you a horizontal shift, reflection, or stretch or compression. So we're going to first start by talking about horizontal stretches and compressions, which we'll see result from multiplying your input variable by a number. Okay, so horizontal stretches and compressions. So multiplying the input variable by some number k will either stretch or compress your graph horizontally, and by how much will it stretch or compress your graph. So it's actually not by k, it's going to be by 1 over k. So the reciprocal of k. So I'll write that down as well. So this is the reciprocal. So remember in the last video, we were talking about how at the very beginning of the video, we talked about how horizontal shifts kind of go backwards of what you'd expect. And we'll talk more about that later in this video. Similarly, horizontal stretches and compressions work a little bit backwards of what you would expect, right? So for vertical stretches, if you have something like 2 times f of x, it just stretches it vertically by 2. If you have 1/2 times f of x, it compresses it vertically by 1/2. It kind of works exactly the way you would expect. For horizontal stretches and compressions, you have to look at the number that's being multiplied with your input variable, and you have to take the reciprocal of that to understand how it's going to affect your graph. And so what we'll see is basically if k is bigger than 1, then that's going to result in actually compressing your graph. Whereas if k is smaller than 1, that's going to result in stretching your graph. And I'll write that down in a moment, but I think if we look at an example, that will kind of make things clearer. So first example, before we get into to working with the trigonometric functions, is just asking if you were to compare the original graph of f of x is equal to square root of x to the graphs of g of x is equal to square root of 2x and h of x is equal to square root of 1/2 x, how are those graphs going to compare? And so basically, g of x is equal to square root of 2x. So what is the k in this scenario, right? K was representing the number that was being multiplied by your input variable. And so in this case, k is 2, right? 2 is the number we're multiplying with our input variable. So that means that this graph is going to be compressed by a factor of 1/2 horizontally. So where am I getting that from? Well, it's this idea of the reciprocal, right? So you look at what number you're multiplying with x, and you take the reciprocal of that, right? So here we have 2, here we have 1/2. that is the reciprocal of 2. And so because it's 1/2, that tells me, okay, it's getting compressed, right? Because it's, if it's becoming 1/2 of the size it originally was horizontally, that means it's becoming narrower. So it's getting compressed. On the other hand, if we look at h of x is equal to the square root of 1/2 x, well, what is the reciprocal of the number we're multiplying with x this time? Well, this time we have 1/2. If we take the reciprocal of that, we get 2. And so that means that this graph is actually stretched by a factor of 2 horizontally. So you're always taking the reciprocal of that number, and that kind of tells you what to expect in your graph. And as I did in the last video, I'm going to link my 141 videos about transformations below. If you look at the one that covers that covers stretches and compressions, I go into a little bit of why this works the way it does, and I'll also talk about it when we get to an example with sine and cosine a little bit more. But yeah, you might want to check out that video. Just to add a little bit more to this, basically the transformation will be a horizontal compression if that number k is greater than 1, and it will be a horizontal stretch if that number k is less than 1. Again, it's just because of that reciprocal idea, right? So you take the reciprocal and that will tell you basically whether to expect it to get larger or smaller. Okay, so let's actually look at an example of this with the graphs of sine and cosine. So we want to sketch the graphs of f of t is equal to sine of t, g of t is equal to sine of 2t, and h of t is equal to sine of 1/2 t. And then we're going to also identify their periods, because the next thing we want to do is kind of make a connection between that number k and how that plays into the period of a trigonometric function. So let's start by sketching the graph of sine of t. So f of t is equal to sine of t. We know that that starts at 0, 0. It hits a maximum at pi over 2, goes back to 0 at pi, goes down to -1 at 3 pi over 2, and then back to 0 at 2 pi. Okay, so that's our original graph. This is going to be f of t. Okay, so next up we have g of t is equal to sine of 2t. So in this case, what number are we multiplying with t? Well, it's 2. So we want to take the reciprocal of that, and that will tell us how much it's been compressed or stretched horizontally. And so because the reciprocal of 2 is 1/2, that means that it is compressed horizontally by 1/2, meaning that it's going to become 1/2 of the horizontal size that it originally was. So what is that going to look like? Well, basically, it's going to take up half as much space horizontally, right? So instead of going through its full cycle between 0 and 2 pi, now it's going to do that between 0 and pi. So we're going to still start at 0, 0, but now the end of the cycle is going to be at pi instead of 2 pi. And so this is where that whole symmetry idea comes in that I mentioned the last time. If you know what the general shape of sine and cosine look like, you don't have to get so fixated on calculating specific points. You can just kind of use symmetry to fill things in. So we know that the graph of sine should go back through its midline halfway between the beginning and end of its cycle, right? So normally that's at pi. Here that would be at pi over 2. And then we know that if it hasn't been reflected vertically, it's going to go up first and then down. And so it's going to go up to its maximum halfway between 0 and pi over 2, which is at pi over 4. And it's going to go down to its minimum halfway between pi over 2 and pi, which is at 3 pi over 4. So just using symmetry and kind of a general knowledge of the shape of this graph to fill in the rest. Okay, so that is our graph of g of t is equal to sine of 2t. So last one we want to do is h of t is equal to sine of 1/2 t. So this time we're multiplying our input by 1/2. And so if we want to see how that affects our graph, we want to take the reciprocal of that number. So this is going to be, if we take the reciprocal of 1/2, that's 2. So that means it's going to be stretched horizontally by a factor of 2. Okay, so what is this graph going to look like? Well, instead of having its cycle go from 0 to 2 pi, if it's stretched horizontally by 2, it should go from 0 to 4 pi, right? So now it's still going to start at 0, 0, but the end of its cycle will be at 4 pi. And again, now we can just use symmetry. So we know that halfway between 0 and 4 pi, it should go back through its midline, which in this case is just the horizontal axis. And then it goes up first. So halfway between 0 and 2 pi is where we'll find its maximum value. So that's going to be at pi. So it goes like this first. And then it's going to go back down and it's going to hit its minimum value halfway between 2 pi and 4 pi. And so that's going to look like this. So now we want to write down, what are the periods of these two functions? Because I want to kind of make a general observation about what the periods of these transformed functions will be. So what is the period of the first one we did, the one in blue? Well, it's pi, right? Because instead of going from 0 to 2 pi, it goes just from 0 to pi to do one full cycle. And then the second one, well, the period got multiplied by 2, right? It got stretched horizontally by 2, and so the period, instead of being 2 pi, is 4 pi. So in general, kind of using that reasoning, like how can we relate k with the period? So what we want to fill out down here is, in general, what is the period going to be if you have sine of k times t or cosine of k times t? So maybe pause and just think if you can come up with a rule. Like, what is the relationship between, if you look at k and you look at the period for these? Like, what is the rule that would allow you to figure out what the period is by looking at k? So I think it's probably easier to see in the first example, the one in blue. So normally, the period is 2 pi, right? And so if we compressed it by 1/2, well, we took 2 pi and we divided it by 2, right? 2 pi divided by 2 gives us pi. And so we did basically 2 pi, the normal period, divided by that number k. So 2 pi divided by 2 gives us pi. And then actually the same rule works here too, right? So if you take 2 pi and divide it by 1/2, dividing by 1/2 is the same as multiplying by 2, right? 2 pi, if you do 2 pi divided by 1/2, that's the same thing as doing 2 pi times 2 over 1, which gives you 4 pi. And so the general rule is always going to be that the period is going to be 2 pi divided by your number k. Maybe let me make this bolder. Sorry. Okay, so that's our general rule for finding the period is you find your number, you figure out what k is, just seeing like what are you multiplying your input variable with, and you just divide 2 pi by that number. So one other thing I want to kind of touch on here is, why is it that things work in the reciprocal way? So, what is it about these horizontal stretches and compressions that causes them to kind of work in a reciprocal way? So why do horizontal stretches and compressions work in a reciprocal way? And I know that's kind of a slightly vague wording, but basically what I mean is, you might, if you had to guess, if you had never learned this stuff before and you had to guess, personally, I would probably guess that sine of 2t would be stretched by 2, right? And sine of 1/2 t should be compressed by 1/2. Like that just seems more kind of natural. But really, I think the best way to understand why this works the way it does is to kind of test out plugging in some numbers. So for example, in the original function, f of t is equal to sine of t. If you plug in 1/2, or sorry, not 1/2, pi over 2 into f of t is equal to sine of t. So if we do f of pi over 2, that would be equal to sine of pi over 2, which would give us a height of 1. So that would be like this point here. So what would we need to, now looking at the blue function, let's think about what number we need to plug into that function to kind of reach that same height, to get that first peak of a height of 1. Well, we would have to plug in pi over 4, right? We can see that in the picture. So why would plugging in pi over 4 lead us to the same height as plugging in pi over 2 did in the original function? Well, let's think about how this function works. So g of t is sine of 2 times t. So whatever number is getting plugged in your original parentheses, that's not the same number as you're taking sine of, right? You're taking sine of 2 times that number. So for example, if you do g of pi over 4, that's going to be sine of 2 times pi over 4, right? Because that's how this function works. It's 2 times t. And so that's going to be sine of pi over 2. And once again, that's going to equal 1. So my point here is that you can plug in a number that is half as large, right? Pi over 4 is half as large as pi over 2. But by plugging in pi over 4, you're able to reach the same height as you did by plugging in pi over 2 in your original function. So that's why it's compressed horizontally. It's like that 2 that you're multiplying t with, it allows you to get away with plugging in smaller numbers for t and still reaching the same height. And so that causes that maximum height to occur earlier, and that causes the graph to be compressed. And then we can see something similar happening in h of t. So notice that h of t reaches its maximum at t is equal to pi. And so that is because if you were to plug in pi, you would get sine of 1/2 times pi, which is sine of pi over 2, once again, which again is 1. So in this case, in order to reach that same maximum, you have to plug in a larger number for t, right? Because you're multiplying it by 1/2, it kind of allows larger t values to reach the same height as the smaller ones did because you're multiplying it by 1/2. And so in this case, we see that bigger t values reach the same height, and so it takes kind of longer for it to reach that maximum, which gives it this kind of elongated shape. So hopefully that kind of explains why these things work in this like reciprocal way. Okay, so let's do another example, or another couple of examples. So next one I want to do is we want to sketch the graph of f of t is equal to cosine of pi times t. So first thing I want to do before we go ahead and sketch it is, first we want to figure out what the transformation is, but then we want to figure out what the period is because that will help us to sketch it. So this one is, well, we don't know yet whether it's stretched or compressed, but we can focus on what t is getting multiplied with. So t is getting multiplied with the number pi. And so that tells us that we want to take the reciprocal of that. So that would be 1 over pi. And if you think about it, pi is bigger than 1, right? So it's going to be compressed. So 1 over pi is going to be making the function smaller in the horizontal direction. So this is compressed by a factor of 1 over pi. And so that tells us that the period is going to be 2 pi divided by pi, right? So remember the rule we learned is that the period is always going to be 2 pi divided by k. So in this case, k is equal to pi, so the period is 2 pi over pi. And 2 pi over pi, well, that's just the same as 2. So this is something that will happen if the number that you're multiplying your input variable with is itself a multiple of pi. What happens is that the period comes out to be just in terms of kind of ordinary numbers, quote unquote. So it doesn't have a pi in it anymore, because the fact that you're stretching or compressing by a factor of pi kind of cancels that pi out in the period and causes the period to just be a number that does not involve pi. Okay, so what is this going to look like? Well, we know that it's going to go through its full cycle between 0 and 2. And so now we want to remember what the shape of cosine looks like. So the shape of cosine, the cycle starts at a height of 1, right? And so we're going to start at 0, 1, and then we're going to reach that same height at the end of the cycle, which in this case, because the period is 2, that's going to be at 2, 1. And then the shape of cosine, it goes down and then comes back up. So it goes down to its minimum point halfway between the two maximum points. And then halfway between each of those, we have the horizontal intercepts. And then we can just kind of fill in the rest of the shape. So you might notice in this video, I'm not going to be kind of sketching the original graphs of sine and cosine in general. Instead, I'm just going to be kind of describing what their shape is like and using symmetry to fill them in, which I think is just kind of a more efficient way to do it. Okay, so next up we have a function that is going to have a little bit more going on. And so this one, it's going to take a little more work to sketch it. I think it'll be a little trickier, but I would encourage you to pause the video and maybe try to sketch it yourself, but at the very least, what I would do is try to identify the amplitude, the period, the midline, see if you can write all of that information down, and then we'll see how we can use all that information to sketch a cycle of the graph. Okay, so what's going on here? Well, first we can see that we have a negative sign, and the negative sign is on the outside of the function. It's not on t, it's on the outside, and so that is a vertical reflection. And the way that I like to think about vertical reflections when it comes to these types of graphs is that it's just going to change the general shape of the function, right? Instead of the function going up and then down, the sine graph is going to go down and then up. So we just need to keep that in mind when we go and sketch it. Okay, what about this number 2? What is that doing? Well, that is on the outside of the function as well, so we know it's a vertical. And so it's a vertical stretch. So remember, vertical stretches and compressions, those ones you don't have to take the reciprocal. It's just going to be a vertical stretch by 2. Okay, what else do we have? Well, here we're multiplying t by pi over 2. And this one actually is I think, a little bit hard to figure out. Well, actually, I guess if you think about what kind of a number pi over 2 is is about 1.5, right? So it's bigger than 1. So we know that if this number that you're multiplying t with is bigger than 1, it's going to compress the graph horizontally. So this is going to be a horizontal compression by 2 over pi, right? You want to take the reciprocal of that number. And you might look at this and be like, I have no idea what that looks like. That's totally fine, because we are able to figure out what the period is, right? And once we know what the period is, you don't really have to worry about how do you draw a horizontal compression by 2 over pi. It will just be kind of encoded into the period. And then the last thing we have here is we're adding 3. And we're adding 3 outside of the function, so it's going to be a vertical change, and it's going to be a vertical shift, right? And vertical shifts work the way you would expect, so plus 3 goes up by 3. Okay, so now that we have all this information, let's write down a few other kind of characteristics of this graph. So because of the vertical stretch, we know that the amplitude has changed, right? The amplitude, remember from the last video, is the measurement from the midline to the highest point on the graph. And so because it's been stretched by 2, the amplitude is no longer going to be 1, it's going to be 2. What about the period? Well, to find the period, we just do 2 pi divided by k. So k is this number pi over 2. So we want to do 2 pi divided by pi over 2. And so to figure out what that is, we can, instead of dividing, multiply by the reciprocal. So that's the same thing as 2 pi divided by 2 over pi, or sorry, times 2 over pi. And so the pi's are going to cancel out, and we're left with a period of 4. So just like we saw in the last example, the period is not going to involve pi. It's just going to be the number 4. And then the last thing we see is that because we shifted the graph up by 3, the midline, instead of being at the horizontal axis, the midline is going to be at y is equal to 3. Okay, so first thing I like to do when sketching these is put down the midline, because that's kind of that's what we're going to sort of treat as our horizontal axis while sketching this graph. And then I like to use the amplitude to figure out what's going to be the kind of max and min of where this graph is going to touch. And so because the amplitude is 2, we know that it's going to go up to above the midline and it's going to go down to below the midline. So it's going to kind of live in this area on the graph that I showed here. Okay, so what else do we need to know about this function? Well, its period is 4. So that means that it's going to go through one full cycle. It hasn't been shifted horizontally, so the cycle is still going to start at 0, but it's going to end at 4. So the period is just going to be 4. Okay, so let's start sketching the graph. So as usual, it's going to start at not 0, 0, but basically at what would have been 0, 0, right? It's going to start at its midline at a t-value of 0. And then it's going to return to that midline at the end of its cycle, right? And so the end of its cycle is at 4. And then it's going to also go to that midline halfway between. So again, I'm just using my general knowledge of what the shape of a sine graph looks like. So there's one more thing we have to remember, which is this has been reflected vertically, right? So instead of, normally sine graphs look like this, instead the graph is going to go the other way. It's going to go down first. And so that means it's going to reach its minimum value halfway between these 2 points. And then it's going to reach its maximum value halfway between these 2. And so the graph is going to look like this. And that's it. So I think it can feel really complicated when you read all these different transformations. It's like, what do those actually look like in the graph? But I think if you can keep track of the midline, the amplitude, and the period, and then just use symmetry, it's really not that bad to kind of fill out the rest of it. One other thing that I should have said earlier in this video, and I did mention in the last video, is remember, this is not the entire graph. We're just sketching one cycle. So, if you were to keep sketching this, you would just see the same shape happening, right? So it would go like this and then go back up, and then here it would be going like this. But because one cycle really captures the whole shape, that's why we're just focusing on sketching one cycle of each of these functions. So next up, we're going to talk about horizontal shifts. So we saw some examples of this with non-trigonometric functions in the last video, but basically adding or subtracting a number, let's call it b, to, or I should say from, it depends on whether you're adding or subtracting, which word you'd use here, the input variable. Is going to shift the graph horizontally by b. And so as we got into a little bit last time, it kind of goes backwards of what you'd expect. And again, if you're curious about why that is, I would definitely recommend checking out my video that I'm linking below about horizontal, or about shifting transformations. So if you look at that video, I definitely go a little bit deeper into why it works backwards. But basically the idea is that if you add a number b, so let's assume that b itself is a positive number. So if you add a positive number b to the input variable, is going to shift the graph to the left by b units. Whereas, again, assuming that b itself is a positive number, so if you subtract a positive number b, that's going to shift the graph to the right by b units. And one other thing that is kind of useful to know here is that in the context of trigonometric functions, horizontal shifts are often referred to as phase shifts. So for trigonometric functions, horizontal shifts are sometimes called phase shifts. So if you see the word phase shift, that just is another way of saying a horizontal shift. Okay, so let's look at an example of this. So in this one, we're sketching the graph of f of t is equal to sine of t minus pi over 2. Okay, so we're adding or subtracting a number from our input variable, right? So we know that it's going to be a horizontal shift. And specifically, here we're subtracting pi over 2. And so that means that this is going to shift to the right by pi over 2. And so when we go and sketch our graph, the shape is going to be the same. The period is still going to be the same, but it's going to start and end at a different point. So the period's still the same, the amplitude's still the same, the midline's still the same, because we haven't stretched anything, we haven't shifted it up and down. The only thing that's going to change is kind of where that cycle begins and ends. So if we're shifting to the right by pi over 2, that means that instead of having our starting point being at 0, 0, it's instead going to be at pi over 2. And so now we just need to, again, figure out where is the end of the cycle. So thinking about the period, we can figure out where the end of the cycle is, and then we can just use symmetry to fill in the rest. So if we add pi over 2, if we add 2 pi to that, that will tell us the end of the cycle, right? Because the period is 2 pi. And so if you take pi over 2 and you add 2 pi, you'll get 5 pi over 2. So that is the end of the cycle. And then it's just symmetry from here, right? So we know halfway in between pi over 2 and 5 pi over 2 is where we're going to go back to the midline. This graph has not been reflected, so it's still going to go up first and then down. And so it's going to hit its maximum halfway between these two. It's going to hit its minimum halfway between these two, and that's it. So key thing with horizontal shifts is really just to remember that the period didn't change. So it's like you're changing where the cycle starts, but you can still just add that period to that starting value to figure out where the end of the cycle would be. Okay, so next up, we're going to get into something a little trickier. So this is now going to be combining horizontal stretches and compressions with horizontal shifts. So let me actually write that at the top here. So horizontal stretches and compressions with phase shifts. Okay, so notice that in this example, we have both a number being multiplied with t, so that's telling us that we have a horizontal stretch or compression, and then we also have a number being subtracted, and so that tells us there's a horizontal shift. So I'm going to do something a little unusual here, and I'm actually going to show you the wrong way to do this. And the reason I'm doing that is not to confuse you, but to really show you why it's wrong. So if I hadn't, if you were just kind of jumping into this example, this is what I think you would probably guess for how this works. So the first thing I think you'd say is, okay, the 2 on this t, that is going to be a horizontal compression by 1/2. And that part is actually correct. So that's why I'm writing it in green. I'm going to write all of the stuff that is not true in red so that it really stands out. So I'll put my little warning sign here and I say this is the wrong approach. Okay, so again, if you were just kind of looking at this without any kind of knowledge about how these things work, you would probably guess that this is going to be shifting to the right. And shifting to the right specifically by pi over 2. It actually, we'll see it does shift to the right, but it's the pi over 2 part that's wrong, right? It's like, okay, well, we're subtracting pi over 2 from t. That should shift to the right by t. So I want to sketch the graph according to that assumption, and then we'll see why that just doesn't really work, why that's not the right approach. So if we're shifting to the right by pi over 2, that means that the cycle would begin at pi over 2 instead of at 0, so it would be like here. And then we're compressing by a half, so that would mean that the period is pi instead of 2 pi, right? So the end of the cycle would be at 3 pi over 2, because that's pi over 2 plus pi. And so, as usual, I'll just fill out the general shape of the sine graph and see that looks like this. Okay, so this is, again, I'm just going to put it all over just like so there's no confusion. This is not the correct graph. So why is this wrong? So one way you can always check, I think this isn't the best way to approach graphing, but it's a good way to check your answer with graphing. So how can you check whether a graph that you drew is the correct graph for the equation you were given? Like, what's a quick way to test it out? Well, you could plug in points, right? And so, for example, here we see that we have the point pi over 2, 0. And so if this graph that I drew is correct, then if we plug pi over 2 into our function, we should get 0 as our output, right? So if I do sine of, so actually let me write it this way. If we do g of pi over 2, that's going to be sine of 2 times pi over 2 minus pi over 2. And so that's going to be sine of 2 times pi over 2 is just pi. So we have pi minus pi over 2. And so pi minus pi over 2, if you do that out, you'll find that that is pi over 2, right? It's like 2 pi over 2 minus pi over 2, you're left with pi over 2. And so what is sine of pi over 2? Well, that's equal to 1, right? If you go to an angle of pi over 2 on the unit circle, the y-coordinate is 1. And so that's 1, and that doesn't match the graph, right? If this was the correct graph for this equation, then it should have equaled 0. So what would be, let's think for a moment, like what would be the correct input that would actually give us a height of 0? Like kind of working backwards, looking at what we went through here, what number would we have wanted to plug in here so that we actually got 0 as our answer? Well, sine of 0 is 0, right? And so we want the stuff on the inside of the parentheses to equal 0, right? If this was sine of 0, then we would have gotten 0. And so what number would give us 0 on the inside of the parentheses? Like what would we want to plug in here, right? This is what you're plugging in for t. It's showing up here. I know it's a little confusing because there's multiple pi over 2s, but this pi over 2 that I just circled in green, that's the one that comes from plugging something in, right? Because our equation is g of t is equal to 2t minus pi over 2. So what number would we want to put here instead of pi over 2 to ensure that all this stuff on the inside of the function actually equaled 0, because then we'd get sine of 0 is equal to 0. Well, if we plugged in pi over 4, it would work, right? So let me write that down. So if we plugged in instead g of pi over 4, then we would have sine of 2 times pi over 4 minus pi over 2. And so if we simplify that, we would get sine of pi over 2 minus pi over 2. And sine of pi over 2 minus pi over 2, well, that's sine of 0, and that is equal to 0. And so that tells us that the graph of g of x, or g of t, should actually contain the point pi over 4, 0, not what we found above. So the graph that we sketched above instead contained the point pi over 2, 0. So does that kind of make sense? Basically just showing you that, first of all, this equation doesn't work, right? The equation doesn't match the graph. And second of all, we can kind of look at what we did over here and kind of work backwards and think, well, what number should have given us that output of 0? Like, where should this point be? It shouldn't be at pi over 2, 0. It should actually be at pi over 4, 0. And so what does that tell us in terms of what the shift actually should be? Well, it shouldn't be pi over 2. It should be pi over 4. So I want to actually show you now what the correct approach is for this. So now we're kind of starting this over. Again, we're working again with the same function. So g of t is equal to sine of 2t minus pi over 2. So what is the correct approach for actually figuring out what that horizontal shift is? Well, we actually have to factor out this number 2. So let me just make it really clear. This is now our correct approach. So if we rewrite this function as sine of 2 times t minus, so how would we rewrite this? Well, if we factor out a 2 from both of these parts, we get t minus pi over 4. And so now we can look and see what the horizontal shift is. So basically, if you're looking for all of this explanation, you're like, well, what's the rule? The rule is that you have to factor out k. Whatever number is being multiplied with t, you have to rewrite it so that number is factored out from both t and the horizontal shift. Only then will you be able to actually see what the horizontal shift is. So now we can look at this and go in and say, okay, this is going to be a horizontal compression by 1/2. Again, that part was correct all along. But now we can say, okay, this is going to be a shift to the right by pi over 4. And so again, like why does that work? It's because of, you can go back to like plugging the number in, right? In order to, because you're multiplying t by 2, in order to kind of get 0 inside of the sine function, which that would correspond to on the normal sine function, like the original point, right? The original or the starting point of a sine function is 0, 0. In order to figure out where that point ends up, you want to be taking sine of 0. And so because you're multiplying t by 2, in order to get 0, you have to kind of figure out like you have to factor the 2 out from both of them. Hopefully that kind of makes sense. If it doesn't, you can just memorize the fact that you have to factor that number out. Okay, so now we're ready to actually sketch this graph. So we're going to shift it to the right by pi over 4, meaning that instead of the cycle starting at 0, it's going to start at pi over 4. We know that the period, maybe let's write that down, the period is going to be pi, right? So where am I getting that? I'm doing 2 pi divided by 2. So you're always taking the period and dividing it by your number k. And so that means that I want to add pi to pi over 4 to figure out the end of the cycle. So pi over 4 plus pi is going to give me 5 pi over 4. So that's the end of the cycle. Then we can just use symmetry to fill in the halfway point, the maximum, the minimum, and together this is going to give us our graph. Okay, so let's write down some kind of general information here. So we've talked about a lot of different types of transformations, and really what I'm about to write down, I hope it doesn't feel like this long list of things to memorize, because if you understand transformations, a lot of these just kind of fall naturally from transformations. Okay, so I want to talk about, how do you find in general the period, phase shift, midline, amplitude, all those different things for a trigonometric function that has a bunch of different transformations going on. So here, by the way, I wrote this out with sine, but it's also true with cosine. I just didn't want to rewrite the whole thing. Okay, so let's start with the amplitude. So what would the amplitude be for a function that is a times sine of a bunch of different stuff. Well, remember this number a is what's telling you the vertical stretch. And so really this number here is what's determining the amplitude. The one thing is that this number a could be positive or negative. And so really we want to say the amplitude is absolute value of a, right? So like, for example, did I do any examples like this in the video? I'm not sure. Probably did one earlier on. Let's see. Here, so when we had -2 sine of pi over 2t plus 3, in this case, following kind of the format that I wrote, this number is a, right? A would be -2, but the amplitude is not -2. The amplitude is just 2. Amplitude should always be positive because it's just like a measurement of distance, and distance is positive. And so you always take the absolute value of that coefficient out front to find the amplitude. Okay, what about the period? So we talked about that earlier. The period is always going to be 2 pi divided by whatever that coefficient is of t. So 2 pi over k. Continuing to move from left to right, we talked about how the phase shift, that's the same thing as the horizontal shift. So that is going to be this number b. But be careful. Notice that in this general formula that I wrote out, k is factored out. So k has to be factored out in order for you to be able to read this off as being your horizontal shift. So maybe I'll make a quick little note of that. So k must be factored out in order for you to actually read that off as the phase shift. And then the last thing is the midline. So the midline we know happens from the vertical shift, right? Because that's what moves the midline up and down. And so the midline is going to be y is equal to c. So whatever that number c is, that's going to tell you what your midline is. So let's do one more example of graphing a function with a bunch of different transformations. So this time, instead of writing down all the transformations, instead of saying, shift by this, reflect by this, stretch by this, let's focus on finding things like the amplitude, the period, the midline, the phase shift, because that's really the information we need to sketch this graph. So in order to do all that, we need to rewrite our function and we need to factor out this number pi, right? In order to make use of these kind of rules up here, that coefficient k has to be factored out. And so we can rewrite this as negative cosine of pi times, and so we're going to have t minus something, right? We need to figure out what goes there. Oops. So how do you figure out what number goes here? Well, basically, I like to work backwards. I like to think about, what would I need to put here so that if I multiply pi times that number, I get pi over 4. And the answer would be 1/4, right? Pi times 1/4 gives me pi over 4. And so we have a phase shift, we'll see, of 1/4. Okay, so let's start to write down some of this, the characteristics of this function. So the amplitude, notice there has not been a vertical stretch. It's been reflected vertically. And so that I actually will make a note of because that's not really included in any of the other information we're writing down. But we need to make note of the fact that this is going to be like an upside down cosine function. So the amplitude is still going to be 1, right? If you take the absolute value of -1, it's still 1. There has not been a vertical stretch. Okay, so next up, we want to figure out the period, phase shift, and midline, right? And so I'm trying to be consistent with my color coding here. Let's see, I think it was green. So the period is just going to be 2 pi divided by the coefficient of t, right? And so that's 2 pi over pi. And so the period is going to be 2. Next up, we have the phase shift. So I'll just use purple for this. So remember, once we've factored out k, then we can just read the phase shift right off. And so it's going to be 1/4. And so notice I'm writing positive 1/4. That's because we're shifting to the right by 1/4. So if we were shifting to the left, we would put a negative sign. Basically, you're flipping the sign that you see here because of the whole way that horizontal shifts work. And then last thing is the midline. So the midline is going to be y is equal to -1 because the graph has shifted down by 1. Okay, so now that we have all this information, we can start sketching the graph. So I'm going to put in the midline, y is equal to -1. And then using the amplitude, well, the amplitude is still 1, so we can use that to put down what the maximum and minimum heights will be for our function. Okay, so now we are ready to start sketching the graph. And so we want to start by thinking about the phase shift and the period. So the phase shift, it's supposed to go to the right by 1/4, which means that instead of starting our cycle at t is equal to 0, we're going to start it at t is equal to 1/4. So maybe I'll make a note of that here. So 1/4 is where we're going to start the cycle. But if we think about what the shape of this graph is going to look like, so normally cosine starts at its maximum height, goes down, comes back up. This has been reflected vertically. And so that means that at the start of its cycle, it should actually be down at its minimum height. So the first point we're going to graph is this point here. Then we want to figure out where the cycle ends. So the period is 2. So if we do 1/4 plus 2, that's going to give us 2 1/4. Or 9/4. And so that's the end of the cycle. And so using kind of this symmetry that we know about this function, we know that it should also be at its minimum height at the end of the cycle. So it should be down here as well at 9/4. So next thing we need to do is find halfway between these two in order to plot our maximum point. So one way that you can do this, I mean, you can count the boxes if you want, that works, or you can also find the average of these two things. But really, let's see, I think in this case, let's just count boxes. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that means that halfway between them should be here. And so that would be this point here. Then the last thing we need to do is find the places where it crosses the midline. And so that's going to happen halfway between the minimum and the maximum of each of these pairs. And so we're going to have one point here and another point here. And so now we can fill this out, remembering that the graph should have a curved shape. And so that's our function. So I know it can be overwhelming with all these different transformations, but again, I think if you put down these kind of guidelines first and use those to help you sketch it, it really isn't as bad as it seems like it will be. Okay, last question I want to do. This one, we're not going to be graphing anything because this is a slightly more complicated example, but we're just going to write down the amplitude, midline, period, and phase shift. Just get a little more practice with that. Okay, so let's start with the amplitude. So we can see that this function is being multiplied with 3/4, and so the amplitude is going to be 3/4. So it's always just that coefficient on the outside because that corresponds to the vertical stretch. Okay, the period we can also find just by looking at it now, but we'll see that to find the phase shift, there's going to be something else we have to do. But the period is going to be determined by 2 pi divided by k. So that's going to be 2 pi divided by 2. So the period is pi. So in this case, we've had a horizontal compression by 1/2, and so that's why the period ended up being pi. Now, in order to figure out what the phase shift is, we actually need to rewrite this function so that we've factored out the 2. So I'm going to rewrite this as 3/4 times cosine of 2 times. So we have t plus, and I'm just going to kind of leave this blank so we can think about what has to go there, minus 2. Okay, so what number has to go here? Well, again, kind of work backwards. Think about what would you need to multiply 2 with in order to get 2 pi over 3? And the answer is pi over 3. 2 times pi over 3 is 2 pi over 3. Okay, so now that we have that, we can actually read what the phase shift is. So this function is going to be shifting to the left by pi over 3, and so we can say the phase shift is negative pi over 3. So remember, you put a sign on the phase shift to communicate whether it's going to the right or the left. And then the last thing is the midline. And so remember, again, the midline is always just determined by the vertical shift. And so in this case, the midline is y is equal to -2. All right, that is it for this video. I definitely recommend doing the worksheet associated with this video. It has a lot of examples, and I think really practice is the best way to get comfortable with these kinds of problems. So in our next video, we're going to be talking about the graphs of some of the other trig functions. We're not going to be spending nearly as much time on those graphs, but we will get at least a little bit of familiarity with them. So I'll see you on the next video.